This is question 8 of the 2018 higher level mock examination. It's a topic 3 question involving calorimetry, where 2 kilograms of ice from a freezer at negative 15 degrees Celsius is mixed with 10 kilograms of water at 30 degrees Celsius. You're asked to find the equilibrium temperature, assuming no losses of energy to the environment. You're also given 3 pieces of information to use: the specific heat capacities of ice and water, as well as the specific latent heat of ice. The approach with these calorimetry questions is about energy transfer, where the energy gained by the cooler substance is equal to the energy lost by the warmer substance. So in this case, all energy gained by the ice in coming to the equilibrium temperature has been lost by the water. The mark scheme asks for this approach and rewards you with a mark for it, either whether it's explicitly stated or just implicit in the way you have set up your equations. With situations like this, and setting up the equation, it's important to determine how many different terms you need on each side of the equation. And one way you can look at this closely is by drawing a heating curve. Here I've shown the ice down here in the solid state, and then the water is up in the liquid state. And I've put the equilibrium temperature and a little bit cooler temperature in the water phase. So for the ice, you can see here that I need to heat that ice up to the melting point, then I need to melt the ice, and then I need to warm that melted ice water up to the final temperature. These 3 different stages here tell me that I will need 3 terms in my equation for the ice. For the water, it is a straightforward mc delta T term for cooling down to the equilibrium temperature. So here I have it set up. Here are my 3 terms for the ice, and here's the energy lost by the water. In setting up the equations, it's important that all substitutions are done very carefully. Here's mc delta T for the ice, here's the ml, and here's the mc delta T for the melted ice water. Realize that the specific heat capacities here are different because of the different phases of matter. On this side of the equation, I've switched around the T2 minus T1 because I need all terms to be positive here for this approach to work. So here I've actually done T1 minus T2 because I know this term will turn out positive. Here's my substitution of the values. Again, here's the heating of the ice. This turns into a plus 15. Here's the latent heat of melting for the ice. And here is the specific heat capacity of water for warming up the ice water. Both of these terms have a final temperature value in them. And once you get this all set up, it is working through the math to get an answer of 10.2 degrees Celsius as the equilibrium temperature. The part B of this question involves the changes of energy in a change of phase and where the energy goes when it is melting. So there are 3 marks for this question, so you must be clear on all 3 points. The first point of the marking scheme is that the absorbed energy is used to break intermolecular bonds in the solid. So that is increasing the spacing or pulling the particles apart. But the term intermolecular is, I think, quite important in its mark scheme to get the mark. The question implies that you should address the fact that there is no change in temperature, so it's important to actually stress that there's no change in temperature because the kinetic energy remains constant. So show that knowledge. And then again, the question is implying that energy is added, but where does it go? So the third statement needed is that the energy is not lost, but it becomes intermolecular potential energy, or I think this term is very important.